I'm forgetting again to turn on the laser pointer, which is not a good thing, but I'm just sitting here in my room and doing these things for my own edification, so sometimes I'm not as careful as I should be about the details. So let's look at a little bit more about the weathering and CO2 regulation. Remember, we are in the long-term evolution of carbon cycle and climate regulation, so these processes are important. And when we go to the future of carbon now in the modern days, then there are many so-called geoengineering approaches which try to pick up on the weathering ideas to draw down carbon dioxide, like spreading broken rocks onto soils, because then you expose more of the rock surface, and with the warming and changes in rain and so on, the weathering rates can go up. There are also ideas to enhance alkalinity, which is also related to weathering and taking out carbon dioxide, etc. And there is debates about whether weathering is more important on land or ocean, and we now know that ocean does play a big role, and whether biological role is important or not. We know we looked in the last podcast at the potential role of generating biology in generating calcium carbonate, and here we are going to touch a little on the role of chemical weathering, where it's not just rain and H2CO3 but also what happens in the rocks on the surface in terms of, let's say, hydrolysis or reaction with water, chemical weathering where oxidation and carbonation can happen. Plants can grow, put roots on rocks, and begin to put carbonic acid into the rock and create loose surfaces that cracks begin to appear in the rocks, and weathering rates are altered. So here is a summary of these kind of feedbacks. Here, long-term carbon cycle and feedbacks with atmospheric CO2. Tectonic activity can increase, obviously will cause uplift and expose material for weathering, like mountain building. Himalayan mountains are still growing and carry some of the highest loads in the rivers, which is part of the weathering process, as well as physical erosion. There is also subduction involved, which can do metamorphosis and hide away carbon, which then gets exposed through volcanic flux, which is related to tectonic activity. Of course, atmospheric CO2 feeds back to temperature, rainfall, and weathering, as well as organic carbon weathering on soils and land, etc. There is silicate weathering, which can have a negative feedback on atmospheric CO2. Uplift's impact on organic burial rates are not always well understood, but organic burial obviously would have a negative correlation with atmospheric CO2. Ocean has a large role to play in terms of carbonate burial and so-called MORB degassing, which is the mid-ocean ridge basalt degassing. Okay, so this is the long-term CO2 reservoirs, and there are feedbacks implied, positive, negative, and there are sometimes plus minus in some places, which means the feedback is neither strongly positive nor strongly negative. Just to raise a challenge, this is from a model that does long-term carbon cycle, and you are going from 600 million years ago to the present, and you are looking at estimates of partial pressure of carbon as a factor of the present levels. Obviously, we have had very high carbon in the atmosphere in the past, which dropped off during the evolution of photosynthetic vascular plants, Devonian, Carboniferous, where lots of coal got formed and buried. Then you had high carbon during the so-called hothouse eras. This is the should be Permian. Permian Triassic, I hope I'm right, and there was the during the extinction of the dinosaurs, there was also high carbon, so-called Cretaceous hothouse, and so on. So this can imply that weathering rates change over time, and it's not easy because it's a very slow process. You need to find proxies to estimate weathering rates. So isotopes like strontium 87 to 86 ratios are used for estimating changes in weathering rates, and the thickness of the curve here corresponds to the uncertainties. So I just want to tell you that weathering rates are not constant. Other than these feedbacks which change the weathering rates, the entire processes have to be estimated for correctly understanding the change in carbon dioxide over Earth's history and its modulation by weathering, which is critical for understanding regulation of climate, especially into the future, which is our goal in this series of podcasts. So looking at a rate factor relative to today, again, the Berner model tries to estimate CO2 changes along the way as relative to present levels, and you can see that there is a high carbon relative to today and high weathering rates. There could be temperature feedbacks, rainfall feedbacks, and tectonic feedbacks. As the weathering rates dropped, the PCO2 went up, and then PCO2 started dropping again, and weathering rates dropped off, and then picked up here more recently, around 300 million years ago or so, because there is the additional biological enhancement factor that has to be included. So biology greatly enhances weathering rates, mostly through the chemical weathering and so on. Okay, so this is something to keep in mind. To look at the reactions, typically you have some divalent cations like calcium plus plus, magnesium plus plus, iron plus plus in the silicate rocks. That's the general formula, which is being weathered into a calcium carbonate, magnesium carbonate, iron carbonate, and I don't know if they have different names, and silica is released. Of course, at the bottom of the ocean, with subduction, ocean crust formation and subduction metamorphosis at high temperatures can combine these to release carbon dioxide, which is reverse weathering, as we will see in the next section. And the biological component of weathering obviously comes through by using photosynthesis, where CO2 and H2O combine to form basic molecules of carbohydrate and sugar and release oxygen. Just to remind ourselves, there are non-oxygenic photosynthesis possible as well, and those reactions go something like this, where photosynthesis means energy from the light is needed, so 6 CO2 plus 12 H2S. So sulfides are used, hydrogen sulfide is used to produce the full carbohydrate molecules to release sulfur and water molecules instead of oxygen. So this is how that would work with different enzymes and pathways. Okay, so oxygenic and non-oxygenic photosynthesis do play a role in the weathering. Weatherability is very critical then in terms of changing weathering rates. Here let's start by looking at key principles of the global carbon cycle and atmospheric CO2. The effect of outgassing. So here is carbon input which is equal to output in equilibrium. So going from low to high, and atmospheric CO2 going from low to high. So if you have increasing outgas, let's say increasing volcanism, obviously you will increase carbon atmospheric CO2. Remember, we invoked it during the Snowball Earth episodes, where we said even if the entire planet was frozen over, volcanic activity would continue and CO2 would build up in the atmosphere and begin to melt or terminate the Snowball Earth episode. Silicate weathering feedback, looking again at carbon input-output versus atmospheric CO2. So if the feedback, so there is the increase in volcanism, the same curve we looked at here. but the feedback with the silicate weathering would depend on whether the weathering rate is high or low. So if it is low, you would go in this direction, and the feedbacks stronger would bring you down to this. Basically that means if the weathering rate is pulling down more CO2, you would cool the temperature and reduce weathering rates and increase atmospheric CO2 and change carbon input and output. Organic carbon and carbonate preservation similarly have an impact on atmospheric CO2 and carbon being sequestered. So increased preservation would increase carbon input and output and reduce atmospheric CO2. I think you know what we are talking about. Basically, if you sequester a lot of carbon in soil or in the deep ocean, that's going to be taken away from the carbon cycle and active carbon pool, let's say in the atmosphere and water. So those rates matter. These are just schematics. Weatherability. So increased in weatherability would also modulate atmospheric CO2. Increased weatherability would change atmospheric CO2 and carbon, total carbon pools. Weatherability obviously depends on the things that we talked about in the feedback picture before. Sorry, going to these processes here. Okay, reverse weathering is where silica is being metamorphized back into silicate rock and releasing a CO2, so that would go in this direction. And marine weathering versus terrestrial weathering would also affect the atmospheric CO2 and carbon in a similar sense as organic carbon and carbonate preservation. So it would pull down for the same atmospheric CO2 level, you would reduce carbon input, which is equal to output in equilibrium. Okay, intuitive things, but just let's go through them anyways. Here is the weatherability. So if weatherability increases, atmospheric CO2 would decrease. So this is not about increasing temperature and rainfall, but directly changing weatherability parameters like mountain building, tectonic uplift, and so on, which would then reduce atmospheric CO2 and then feed back to temperature and rainfall and further feedback to weatherability, right? For example, uplift rate would increase, weatherability would increase, but the soil residence time would decrease because you have fraction of primary minerals in the rock and in the soil and bedrock interacting with each other, and based on the uplifting rate, which we are looking at here, the exchange of primary minerals and weatherability of the terrestrial surfaces would change. So here this is showing heavy rocks and lighter rocks, so magnesium, iron, mafic rocks and feldspar, aluminum, carbonate, silica type rocks, which are lighter. Their ratio would also determine weatherability rates, weatherability of the Earth for the same temperature and CO2 levels and precipitation. What would be the weathering rate? That's what we're talking about here. And biological alteration. Weatherability is obviously affected by biology because that's part of the chemical weathering. So role of chemical weathering in long-term regulation is a critical player in the regulation of carbon cycle and climate over long time scales, and life has continuously evolved over this time scales we are looking at, let's say from even the Precambrian 540 million years ago to now, the evolution of plants, mammals, bigger animals, increasing oxygen, body mass size, and so on. There are faster time scales and slower time scales. So the plants evolving and colonizing land and growing taller and quickly drawing down carbon through photosynthesis obviously led to a cooling Carboniferous, where a lot of plant hydrocarbons got buried as coal and so on. They are all interacting with carbon cycle silicate weathering cycle, and climate. So the co-evolution of all these three is what we're interested in, because, as we said, as we go into the future, we want to understand how these interact at various time scales and how geoengineering can exploit some of the natural processes as well.